All right, so this is the other way of solving exponential equations, and we're going to use logarithms. This will work on any of the things from the previous video as well, but some of the stuff in this video will not, cannot use the previous method. So this method works with everything, but the other method does not work with everything. Okay, so the whole idea here is to isolate the exponential. Right, and we've done this with a lot of equations. When we're solving square root equations, right, we get the square root by itself. When we're solving, and that's actually the biggest one that jumps to mind. When we're solving logarithmic equations later on, we're going to get the logarithm by itself, okay? But a lot of things, when we have complicated functions, we get the complicated function by itself and then undo it with inverses. And the inverse of an exponential is a logarithm. All right, so example 2. Solve. Part A is going to be 8 to the x minus 7 is equal to 1. And we could do this one with the previous method in the previous video, right? We could rewrite the right-hand side as an exponential. 8 to the 0th power is equal to 1, and then set those exponents equal to each other. Or we could undo this. How do we undo an exponential? We take the logarithm. We convert this to logarithmic form is another way of doing it. So we're going to take log base 8 of both sides because our exponential has base 8. All right, you could use any base actually, but log base 8 is the easiest. Now, let's use the inverse property from the previous section to simplify the left-hand side. Log base 8 and 8 to the x, these are exponential functions, they cancel. Left-hand side cancels to become just the exponent. Right-hand side, we can evaluate. Log base 8 of 1, we can evaluate that. Sometimes you won't be able to evaluate that, and then you'll have to either leave it as an exact answer or you can plug it into your calculator with the change of base formula to get an approximation. But log base 8 of 1 is 0. So x minus 7 equals 0. Add 7 to both sides. X is going to equal 7. And you should be able to check your answer, right? If you plug in 7, 7 minus 7 is equal to 8 to the 0, which is equal to 1, which is our right-hand side, which is exactly what we wanted to show. All right. And we can make these as complicated as we want. 2e to the 3x plus 1 is equal to 5. And for these, I will want an exact answer. So give an exact answer. Some of them we're going to approximate, but unless it says approximate, we're going to give an exact answer. So get this exponential by itself, right? That's a summary of this whole video. Isolate the exponential. So exponential function, we need to get it by itself. We need to subtract 1 from both sides. We get 2e to the 3x, subtract 1 from both sides, is going to equal 4. Still not isolated, it's got a 2 in front. Divide both sides by 2. E to the 3x is equal to 4 divided by 2. 4 divided by 2 is 2. Now we undo the exponential with a logarithm. And you can use any logarithm you want. But here I think the natural logarithm makes most sense. Natural log, because that's log base e. So natural log of e to the 3x is equal to the natural log of 2. And just like last time, these are going to cancel completely. They're inverse functions. And the left-hand side cancels to just become that exponent. We get 3x is equal to the natural log of 2. Unlike last time, we can't simplify this right-hand side. The natural log of 2 is an irrational number. It's a decimal that keeps on going forever. So if we wanted to approximate, we could plug that into a calculator. Because I want an exact answer, we're just going to divide both sides by 3 and say we have the natural log of 2 divided by 3 as our final answer. So checking your answer here is a little trickier, but you can still do it. You can do it with a decimal approximation, which will give you a close check, or you can check it with the exact answer and you'll get exactly that it checks out. All right. And I'll show that off with a later example. Let's do some more of these. 2e to the 3x plus 1 equals negative 2. This is not deja vu. You have seen something very similar. B is a very similar problem. Let's see what a slight change is going to do to the answer. Subtract 1 from both sides. 2e to the 3x is equal to negative 3. Isolate that exponential function. Divide both sides by 2. E to the 3x is equal to negative 3 halves. Now there's two things going on here depending on how you want to look at it. The first thing going on here, this is an exponential function. We've isolated the exponential function. Any isolated exponential function like this has a range of 0 to infinity. We only get positive numbers as our output. So when is this exponential function equal to a negative number? Never. If you can recognize this here, you can stop. But let's say I'm not good at domain and range hypothetically. We keep on going. Take the natural log of both sides. Natural log of e to the 3x is equal to the natural log of negative 3 halves. And again, we got another warning sign right here. This does not exist. The domain of a logarithm is positive numbers. This guy right here, this does not exist. All right. So there's no solution. X is going to equal something that doesn't exist. No solution. Watch out for your negatives and domain and range. Okay? So that's what we're going to do right there. Let's do part D. Part D, 2 to the x plus 1 equals 6 to the 2x minus 1. Now, this one's pretty tricky, so watch out. The whole goal, I said for this video, is to isolate your exponential function. But notice right here, we've got two exponential functions. So when we take the log of both sides, you can choose. Do you want to use the natural log? Do you want to use the common log? Do you want to use log base 2? Do you want to use log base 6? And all of those answers are good ones, okay? You can use any logarithm you want here. In the other ones, if there was only one exponential function, you choose the base that matches the base of the exponential function. But here, it doesn't really matter. All right. So let's do the natural log. Let's do it two ways. We'll do the natural log on one side, and we'll use log base 2 on the other one, just to compare contrast. So if you use the natural log on both sides, this is what we get. So use properties of exponentials. The exponent comes down in front. So we're going to get x plus 1 is our exponent, and that gets multiplied by the natural log of 2. We do need parentheses here, right? The whole exponent gets multiplied by the logarithm. And the same thing happens on the right. The exponent comes down in front, and we have natural log of 6. Now this looks super ugly, but remember, we're just trying to solve for x. So everything that's an x, we want on one side. Everything that's not an x, we want on the other side. So we're going to have to distribute on both sides so we can get those x's by themselves. So on the left, we're going to have x times the natural log of 2 plus 1 times the natural log of 2. On the right, we're going to have 2x times the natural log of 6 minus 1 times the natural log of 6. Still looks kind of bad. But let's get everything with an x over here. Let's get everything without an x on the other side. So this natural log of 2, we need to move over. This natural log, this guy, we also need to move over. So we're going to get x times the natural log of 2. Let's subtract this one over. So minus 2x times the natural log of 6. We subtracted this guy over, minus natural log of 2, and we still have the minus natural log of 6. So everything with an x is on one side, everything without an x is on the other side. We're very close. To solve for x, we need to factor the x out so we can divide by what's left over. So if we factor out an x, we're left with the natural log of 2 minus 2x. Oh, that's not it. This is why you don't do math in pen. You get the natural log of 2 minus 2 times the natural log of 6. All right? Like so. And the right-hand side is the same. Okay. I'm going to factor out a negative of the right-hand side just to have things be a little bit more positive looking. But excuse me. He didn't like that. All right. And now to solve for x, we divide by what's being multiplied by x. All right. So x is going to be that right-hand side, which is natural log of 2 plus the natural log of 6 divided by this coefficient on the left-hand side, which is natural log of 2 minus 2 times the natural log of 6. There's a couple ways that we could rewrite this and a couple ways that we could simplify it, but this is pretty good. All right. Again, there are a lot of ways to simplify this. I don't care whether you do or not. I'll accept this as a final answer. But one way that you could simplify this is to combine the logarithms, right? You could say, okay, what is the numerator? Natural log of 2 plus the natural log of 6 is the natural log of 12. Remember, if you add two logarithms together, it's like multiplying their insides. And on the bottom, that's the natural log of 2 minus the natural log of 6 squared, which is 36. And then you could keep on going with this way and simplify it some more. But I don't need it, okay? This is fine. This is a fine format to keep it in. And you could have also taken the log with a different base, and you're going to get something that looks different, but it's going to be the same thing. Okay. And for time purposes, I don't think I'm going to do it in this video because it's already going to be a very long video. We have two examples left. One of them is going to take a bit. So let's look at part E. All right, part E. Can it be 5? No. That's the next example. Part E is going to be e to the 2x minus e to the 1x minus 132 is equal to 0. Now we've got a real problem. Isolate the exponential functions. Sorry, I actually want to talk a little bit more about part D before we go on, okay? Remember that one of the ways to check our answers is to plot the left-hand side and the right-hand side. The left-hand side, right, is y is equal to 2 raised to the x plus 1 power. The right-hand side from the previous example was y is equal to 6 raised to the 2x minus 1 power. All right, so we can graph both of these and see where they intersect to check our answer. So this says at about 0.86. All right, it's a rough answer. And we can check our answer. Is it about 0.86? So if we plug in what we have negative natural log of 2 plus ln 6 divided by ln 2 minus 2 times ln 6. And again, we get that 0.86. So we can visually see that these two exponential functions are equal to each other at the solution that we found, which was, it showed up here, but it went away. All right. So that was weighing on my mind, that last problem, because it looked kind of funny. For this one, the idea is that we can't isolate a single exponential function, and we can't use the method that we used in the previous problem. Because if we took the logarithm of both sides, we have subtraction inside the logarithm, which really causes us some problems. So what we're going to do for this one is a substitution, okay? And this is just a trick. You have to be able to see it, okay? So if you see something like this, it's going to be the same method that I'm going to use here. And this can get really messy. So strap yourselves in because some of these look pretty funky. So the idea is we want to use a substitution. Let u be e to the x. Okay. You say, well, how is that helpful? What about e to the 2x? Well, let's use u squared. U squared is e to the x squared, right? And now we have an exponential raised to an exponent. You multiply those exponents together, you're going to get e to the 2x. So notice e to the 2x, that's our u squared. Minus e to the x, which we said was u. Minus 132 is equal to 0. And look what we've got here. If you missed chapter 2, you want to go back to chapter 2. Well, chapter 2 has come to you. All right? We use a quadratic equation. So we're going to have to solve this quadratic equation with factoring, by completing the square, by using the quadratic formula. You have options. Okay? So you can try to factor. And maybe this one factors. We can check a couple pairs, or you can just always use the quadratic formula. Quadratic formula will always work. But if you wanted to check if it factors right, we need something that multiplies to negative 132, that adds to the middle coefficient, which is negative 1. All right, maybe there's something, maybe there's not. You just have to check the pairs. Okay, but I'm going to show you how to use the quadratic formula on this one. So the solution is going to be u is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Be very, very careful in your simplification steps. Okay, so a is the coefficient of our squared term. The coefficient's 1. B is the coefficient of our linear term. Minus u means the coefficient is minus 1. And c is the constant at the end, which is minus 132. Woo! So let's plug that in. Negative b, the opposite of b is positive 1. Negative, negative 1. All right. And yeah, you can totally remember this by singing yourself a little song. There's a lot of songs about this, but one of them is what? Usually y equals, or x equals. You go, x equals negative b plus or minus the square root b squared minus 4 times ac, all over 2a. You can sing your nice little Pop Goes the Weasel song. Plenty of YouTube videos can do it better than I do. It's an easy way to remember. All right. So b squared, what happens when I square a negative 1? It becomes a positive 1. Minus 4 times a, which is 1, times c, which is negative 132. All over 2 times a, which is 1. And we got to simplify this. And even after we simplify it, we're not done. Okay? And this video is just going to get longer and longer. So we get 1 plus or minus the square root. I'm going to simplify the inside with a calculator. Okay? The inside is 1 minus 4 times 1 times negative 132. Okay, that's going to be 529. All divided by 2 times 1. All right? And 529 turns out to be a perfect square. So as you're doing the quadratic formula and you get here, especially if you get some big numbers, if you think, maybe this is a perfect square, maybe not, just try to plug it in. Plug into your calculator the square root of 529. And if you get a really long decimal, well, you're out of luck. This one, it is just 23. Okay? So let's do this on the next page. 1 plus or minus 23 over 2. So because we have a nice number, relatively, we can split this up into 2 answers, right? It's going to be 1 plus 23 over 2, and it's going to be 1 minus 23 over 2. Well, that's just 24 over 2, and negative 22 over 2. Simplify those out, that's going to be 12, and negative 11. So this tells us that, yeah, we could have factored it. Our answers being rational, fractions or integers. Our answer being rational means that we could have factored it. But the quadratic formula will always work, and sometimes it's not going to factor. And so you might say, hooray, we're done. Our answers are 12 and 11. But remember, this is what u is. The problem didn't have u's, right? Where do we come from? U is e to the x. So replace u with e to the x, right? Because u is equal to e to the x. So u is equal to 12. And u is equal to negative 11. But u is e to the x. So we have to substitute back. If we substitute forward to solve the problem, we have to also go back at the end. All right. And we have to solve each of these. So we're solving this exponential equation, and I've given you 2 more exponential equations to solve, but these ones are much quicker. Undo the exponential with the natural log. We get the natural log of e to the x is equal to the natural log of 12. Left-hand side cancels out. X is equal to ln 12. The right-hand side, negative 11 is not in the range of the exponential, but let's say we forgot that. The right-hand side is the natural log of e to the x is equal to the natural log of negative 11. And you go, whoa, I can't take the natural log of a negative number. All right. There's no real solutions to this one. Finally, we have an answer. X is equal to something. All right. And you can check your answer right here. X is equal to the natural log of 12. If x is equal to the natural log of 12, does this check out? Plug it into your calculator. What do we have? We have e raised to the 2 times x, which is ln 12, minus e raised to x, which is ln 12, minus 132. Oh, it's equal to 0. We did it right. Good. And that's how you do these problems. And these can be a pain. So be very careful and make sure to check your answer at the end. All right. All right. This video is way too long, but I'm going to do another. I figure if I make a video too long, you can always just stop watching it. We're going to do another example just to make sure that you have these examples ready to look at the homework. All right. Example 3. Solve. And this time, I want you to approximate. Approximate to the nearest 10,000th. So remember how many decimal places that is? The nearest 10th, nearest 100th, nearest 1,000th, nearest 10,000. So, okay, 10,000th is 3 zeros after the decimal. Okay, so 4 decimal places is another way to phrase this. All right, we have 5 e to the 2x minus 1 plus 3 equals 15. We solve this the same way we've been solving other stuff. We just approximate at the end. Okay, so get that exponential by itself. Subtract 3. We're going to get 5 e to the 2x minus 1 is equal to 12. Divide by 5. E to the 2x minus 1 is equal to 12 fifths. If you wanted to write this as 2.4 as a decimal, that's fine. Natural log both sides. The natural log of e to the 2x minus 1 is equal to the natural log of 12 fifths. And here's my warning. If you're approximating, whether in this class, another science class, or whatever, most of the time, it's best to not approximate until the very end. If I approximate now, and then I approximate again, and approximate again, all these approximations compound your rounding error. So approximating at the end is a really good idea. So left-hand side, these cancel their inverse functions. We're just left with 2x minus 1. Right-hand side, we're going to leave alone for a bit. Add 1 to both sides. You get the natural log of 12 fifths plus 1. And divide by 2. So x is going to equal the natural log of 12 fifths plus 1, all divided by 2. And now we're going to plug this into our calculator and round to the 4 decimals. Okay, so we plug that in, we get the natural log of 12/5 plus 1, all divided by 2. That's going to equal about 0.9377. And we can check our answer here too. Let's plug in 0.9377 and see if it checks out. So it should equal 15 when we plug it in. Let's see what we've got. We've got 5 times e raised to the 2 times x, which again is 0.9377, about, minus 1, plus 3. This should equal 15. Kind of small on your video. It's close, but remember we rounded. And the better our rounding is, the closer it's going to be to 15. But again, it's really close, 14.999. I'll take it. Okay, so we're close. If you round, you're not going to be exact, which is what rounding is all about. Okay, 26-minute video. This is probably the longest video of your whole semester. All right. The other ones will be much shorter.